We started with a cube and a cuboid and then went on to discuss some more familiar shapes till we finally arrived at one of the most common 3D shapes, a sphere. And now that you have understood the surface areas and volumes of each of these shapes, I can proudly say that you have a head start against those who haven't understood properly. Now, having a head start is good, but to win the race, you need to keep pushing till the very end. That's exactly why we are here. But it is you who will be solving them one by one. I'll just show you the way. It is you who has to scale the mountain. The flag at the top will of course bear just your name. So, ready to conquer new territories? Let's roll. By now, you are well versed with the problem videos, so you know that we recapitulate the important formulae first. Since this video isn't based on any specific shape, it's better that we do a quick revision of all the different formulae for all these shapes. It's going to need some space on the screen, so I am going to exit. You pause the video and go through them properly so that you can be sure that each one of them is at your fingertips. So, here they are. Done? Great! You seem prepared for this one. So, let's not waste time and begin solving. Here's the first question. It states that a cylinder is inside a cube touching all the faces of the cube, and a cone with the same base and height as the cylinder is inside the cylinder. All we have to do is find the ratio of their volumes. You see, there are three shapes in the same question. There's a cylinder, a cube, and even a cone. That's 3 in 1. Anyway, let's break down what the question is asking of us. It talks about a cylinder which is inside a cube, and the dimensions are such that the cylinder touches all the faces of the cube. So, let's take a cube of any edge length and let's put a cylinder inside that touches all the faces. Clearly, this is the largest cylinder that could have fit inside this cube. Now, the question also talks about a cone that's inside the cylinder having the same base and height as the cylinder. So, let's take such a cone and put it inside the cylinder. See, we have all the three shapes in the arrangement we need. As per the question, we need to compare their volumes, right? So, what do we need to find the volume of a cube? Just the edge length. Similarly, to find the volumes of the cylinder and the cone, we just need each of their radii and heights. Lucky for you though, this cylinder and cone have the same height and even the same base, which indicates that they have the same radius. All we need to do is establish a connection between the basic terms of each of these shapes. Use that information to calculate each of their volumes and then finally compare those volumes to get the required ratio. Understood the approach? Great! I will just help you see how the first step works. You can assign a variable to any of these basic terms. It could be the edge length of the cube, or it could also be the radius or the height of the cone or the cylinder. I would like to start with the edge length. So, let's say the edge length of this cube is A units. What then would be the radius of the cylinder? Well, the cylinder touches all the faces of the cube. So, this indicates that the cylinder has the same diameter as the edge length of the cube, which is A units. Thus, the radius of the cylinder is A by 2 units. It's kind of intuitive and the diagram makes it obvious. It is also evident that the height of this cylinder is the same as the edge length of the cube, which is of course A units. Now, because the cone has the same radius and height as the cylinder, its radius is A by 2 units and its height is A units. See, you have all you need. Just use these available basic terms in the respective formulae and you'll be able to find each of their volumes. The fun part is, you don't have to find the volumes of both the cylinder and the cone. If you remember the video on volume of cones, you would know that the volume of a cylinder of radius r and height h is 3 times the volume of a cone with the same radius and height. So here you can find the volume of only the cone and then multiply it with 3 to get the volume of the cylinder. Once all the volumes are known, you can easily compare them to get the required ratios of the volumes of cylinder and cube, cylinder and cone, and even cone and cube. Make sense? Great. It's time that you pause the video and give this question a try. In case you get stuck somewhere or you need to verify the answers, just go through the solution that will appear on the screen. The watch is ticking. Start now. Done! Wow! Did you also get 11:42, 3:1 and 11:42? Perfect! I hope you are enjoying this exercise. Let us now ace another question. Say this one. It states that the radii of the internal and external surfaces of a spherical iron shell are 3 cm and 5 cm respectively. If it is melted and recast to form a solid cylinder of height 2 by 3 cm, find the diameter of the cylinder. Sounds tricky, isn't really? Let's visualize. The question talks about a spherical shell with different inner and outer radii. This indicates that the iron shell has some thickness, pretty much like a coconut. Now, the inner radius, say Ri, is given as 3 cm and the outer radius, say Ro, is given as 5 cm. So, this is how your spherical shell should look like. Now, this shell is melted and recast into a solid cylinder of height 2 by 3 cm. Now, what quantity do you think remains unchanged when we melt a shape and form another? The surface area or the volume? Well, surface area is directly dependent on the surface, right? So, as the surface changes, the surface area would also change. But because we are melting this iron shell and using all the iron collected to form the new solid cylinder, it's but obvious that the volume of iron remains unchanged. So basically, the volume of iron present in this iron shell is the same as the volume of the cylinder that would be formed by melting the iron in the shell. Hey, you have solved enough questions of this type, so you know that to calculate the volume of iron that makes up this spherical shell, we need to find the volume of just this part because the rest is empty. For that, we need to find the volumes of the outer sphere and the inner sphere, which are going to be 4 by 3 pi Ro cubed and 4 by 3 pi Ri cubed respectively. Once both these volumes are known, we can subtract them and the difference will give us the volume of iron that makes up this spherical shell. Make sense? Great. Now, once the required volume of iron is known, we can use it as the volume of the solid cylinder in the formula pi Rc squared into Hc. Here, Rc is of course the radius of the cylinder and Hc is the height. Now, Hc is already given as 2 by 3 centimeters. So, on substituting that and then making Rc the subject, we would get the radius of the cylinder. And once the radius of the cylinder is known, we can just double it to get the required diameter. Understood the approach? Great. Let's list down the steps. First, we find the volumes of the outer sphere and the inner sphere. Then, we subtract the latter from the former to get the required volume of iron. Next, we use this volume of iron as the volume of the cylinder with radius RC and height HC. We substitute the value of HC and make RC the subject of the equation to get the radius of the cylinder. The final step is to just double the obtained value of RC to get the required diameter. So, now that the steps are crystal clear, it's time that you pause the video and try to solve this question. In case you meet a dead end, you can always check the steps in the solution that will appear on the screen. So, get your pens and papers ready and give this question a try. Done? Great! I hope you got the answer right. And even if you didn't, that's alright. You just need some more practice. By the way, why do you think we practice so much? Well, the essence of practicing anything is to meet varied forms of challenges, make mistakes and succumb to those challenges, but most importantly, learn from those mistakes so that they are never repeated again. That's actually your takeaway. To make mistakes while solving problems, but learn from those mistakes so that the same ones are not repeated. You should always make new mistakes. Lucky for you, the opportunities for making new mistakes lie in the coming videos. So, learn from Bill Gates and make the most of your opportunities. I'll be waiting for you in the next video. Till then, keep making mistakes, but most importantly, keep learning from them.